God bless you. God bless you again. God bless you third.
Did that make you happy, Mr. Gordon?
I'm just smiling. We're going to miss it when it's gone.
That was the last.
All right, so today we're going to talk about sections 15.1 and 15.2. In 15.1, we're going to talk about exponential and logistic functions. So we'll start with a definition. Just scroll back here. There we go. Nope, that's not the scrolling back far enough. So we say exponential function can be written in the form y equals a times b to the x. But we have a couple of criteria here for a and b. We say a can't be 0. What would happen if we allowed a to be 0? We had a times b to the x. What would happen if we let a be 0? You just have y equals 0. That's a constant function. That's not exponential. We don't want to include that. We also don't allow b to be 1 or 0. What would happen? Obviously, if b is 0, then or 0 again. But what would happen if b is 1? Right, so 1 to the x is just 1, and then times a is a. That's a constant function again. That's not what we want. And then the last piece is that b has to be greater than 0. I'm going to write it that way and just get rid of the not equal to 0 and just say greater than 0. What would happen if we allow b to be negative? This is harder to see what the issue is going to be. So here's the answer. If we let b be a negative value, x, the exponent, can be anything, right? So x could be 1/2. What is a negative number to the 1/2 power? A 1/2 power is the same as a square root. And can we square root negatives? No. And in addition to just all the denominator 2 fractions, any even denominator is, you can't do the 4th root or 6th root or 8th root of a negative. So how many discontinuities is this thing going to have? Like infinitely many. And oh my gosh, I don't want to mess around with this. Like this is now a nightmare looking to me. It's like nightmarish looking. Obviously, we don't want to include that, right? Because this is now like something that doesn't resemble anything else. It's just got like infinitely many discontinuities. I don't even know if they're removable or vertical or jumps or what they're looking like. Ugh. So that's the justification there. A key feature to all exponential functions is they all have a horizontal asymptote. And the ones in the form y equals a times b to the x, that horizontal asymptote is always at y equals 0. As a piece of vocab, the a we call the initial value, and b we call the base of the exponential. So just some vocab. A note here. So let's say we have y equals 2 times 3 to the x. Is that the same thing as 6 to the x? Jacob said no. If anyone disagree with no?
No.
It's a no. Now, when can I multiply?
After that.
What's that?
After that.
If they have
When can you multiply?
same
So if they have the same exponent,
Are those in a
we can multiply the bases.
process?
And what's the other situation where we can multiply? If they have the same base, we can multiply by adding the exponents. Those two things are fine. But if the bases are different and the exponents are different, no bueno, nothing you can do. This is one of the most common mistakes I see these students making over and over and over again. It'll be a nightmare for you this chapter if you can't get that straight as to when it's okay to multiply two numbers together. That's why I'm taking a moment right now and really just kind of like hammering on this a little bit, even though you might be thinking like, "Durr," but we just want to be careful. All right, example here. So suppose we have just some exponential function. Say that exponential function is f of x equals -2 times 4 to the x. So if I want to do f of 2, what do I do? What is f of 2 telling me to do? Great, so we're plugging 2 in for the x into that equation. So what's the first thing I should do in this -2 times 4 squared? The exponent, good, and 4 squared is 16. And then -2 times 16 is -32. So if we do f of 0, what is 4 to the 0? Not 0. It is 1. So the rule is anything to the 0 power is equal to 1 except for 0. What's 0 to the 0? It's not 0. It's not 1. It's not a negative.
No answer.
It is undefined. It's undefined. It's like dividing by 0. It's bad juju. All right, f of -3. How do I do 4 to the -3? What does that negative exponent mean?
-4.
Yeah, it means a reciprocal. So that's going to be -2 times 1 over 4 to the +3rd. 4 to the 3rd is 64. What's -2 times 64? -2 times 1 over 64, excuse me. Just -1 over 32, right? You just reduce the fraction. Okay. So f of 1/2. How do I do 4 to the 1/2? What's an exponent of 1/2 mean? Yeah, it means a square root. And the square root of 4 is 2, and then -2 times 2 is -4. How do I do 4 to the 3 over 2 now? How do I do that? That looks weird. I'll give you a hint. I'm going to use the exponent of an exponent property. So 3 over 2 is the same thing as 1/2 times 3, right? So that's what I'm going to write this as, then 4 to the 1/2 to the 3rd. Now 4 to the 1/2 is just the square root of 4. The square root of 4 is 2. 2 to the third is 8. And negative 2 times 8 is negative 16. Question so far? Okay. So what if I wanted instead to take some x and y values and find or recover from it the exponential function? So it tells us the table below gives values for an exponential function. Find the equation. So since it's exponential, I know it's got to look like this. Now this problem can be really easy or a little bit more difficult depending on the values that you're given in the table. What separates the two types of problems is if one of my x coordinates is 0. That's the key to making this a much easier problem. So if I use that point, I'd say 3 is equal to a times b to the 0. Everybody's okay there? What's b to the 0? Well, careful. How do I know that b can't be 0? Right? Because 0 to the 0 is undefined. Do we know that b can't be 0? Not because y equals 3. Because it's an exponential function, right? Then we define it so the b can't be 0. So there's that. So a is 3, right? Everybody cool? Okay. So what I'll do now is I'll take a second point, any point I want. I'm going to pick this one because the numbers are most convenient. I'm going to plug back in for a, 3, and now I can just solve for b. Real easy, right? So I divide both sides by 3. I get b is 5. So my function y equals 3 times 5 to the x. Can I say that's just 15 to the x? No. Very good. Good quick reaction on that. Immediately knew I was trying to trick you. Good. All right. So that wasn't so bad, right? Pretty straightforward, rather easy. No big deal. Mr. Kulik, you hinted at that if you weren't given 0 as an x value, that this is a little bit harder. Can I see an example where that happens? Why, yes. I have one loaded up ready to go right now. All right. So again, we know it's an exponential function. I'm not given a 0 as any of my x's. So, well, I guess I'm just going to plug in a point and see what I have, and maybe that'll give me some idea. So I plug the first point in. I have two variables in one equation. I can't solve for a variable with that. Well, maybe if I plug the other one in, something good will happen. I don't know. Nope. Still two variables in one equation. But now I have two equations with two variables. If I treat that as a system, I can solve this. Remember, to solve a system, we typically use substitution or elimination. In this case, I'm going to use elimination. But the elimination I'm going to use is going to be a little bit different than the elimination we did before. Because in Chapter A, our variables in our equation are always being added or subtracted to one another. Here, the variables in our equation are being multiplied together. So instead of adding two equations together to eliminate the variables, I'm going to divide the two equations by each other to eliminate the variables. So I have a choice between equation A or equation B as to which one I want to be the numerator of that division problem. I always pick the bigger exponent of B to be the numerator. So that would be equation B, because -1 is bigger than -3. So if I do that, I have 12 over 48 equals a times b to the negative 1 over a times b to the negative 3. Well, what's 12 over 48 reduced to? 1/4, I heard somebody mumble, I think. And how does a times b to the negative 1 over a times b to the negative 3 reduce? Well, we can do that, right? And then maybe you remember this property of exponents, that to divide two exponents, I subtract their exponents. So that would be b to the negative 1 minus a negative 3, b squared. To solve for b, then I square root both sides. When I square root both sides, I get plus or minus. Oh, that's weird, Mr. Kulik. Are you telling me I get two answers to this? Yeah, we remember that, again, b has to be positive. So I'm going to dump the negative. And now I have my answer for b. Now that I have that, I'm going to take one of the two equations. It doesn't matter which one. I'm going to pick equation b because the exponent is small or is easier to deal with. And I'm going to use that to solve for a. What is negative, or what is 1/2 to the negative 1? 2, right? The negative 1 makes a reciprocal. So I get that a is just equal to 6. I put them together. Whoa, boy. Where'd you go? So far, so good? Okay. Now I want to make a note here, because when I have an exponential that involves a fraction, it's really important that I put a parenthesis around the fraction. The reason is this is 1 to the x over 2 to the x. This is just 1 to the x over 2 to the first. So you need to make sure you're putting a parenthesis around any fraction that has an exponent on it, because they mean two different things. Is everybody cool as to why I'm going to be picky about that notation? Communication is important when you got to mean what you write down. Bless you. Yeah, I almost thought you were Nico there with the sneezing. All right. So we've seen that this value for b could be a bunch of different numbers, right? We've seen examples of it over and over and over again. There's one number in particular for b that'll be especially important, and I'll tell you why in a few minutes here. But that special number is called the natural base, or often Euler's number. That's an irrational number. The irrational number is 2.6 or 2.7182818, yada, 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 goes on forever, infinite decimal, never repeats, much like pi was. Just like pi, where we don't write down 3.1415, yada, 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 we just use the symbol pi to abbreviate it. Here we're going to use the letter e to abbreviate this irrational number. It's beyond the scope of this class for me to discuss like why this number is special in particular and where it really comes from. But let's just say that this number happens to tumble out unexpectedly in a lot of situations in both mathematics and describing natural systems, which is somewhat surprising that this number falls out over and over again when you're like, like counting the number of seeds in the spiral of a sunflower or something, which is an odd place for like this really specific seeming number to just kind of tumble out of things. So one reason that we're of interest in this natural number e is because if I have two exponentials and I want to compare them, often the thing that I really want to compare is how fast one is growing relative to the other. It's much easier to do that if I can write those two exponentials so they have the same base. When I do that process to rewrite them so they have the same base, the base I typically choose is e. So I'm going to introduce another definition for a way to write an exponential function using e. So we could also write our exponential function as f of x equals a times e to the k. Again, a and k are non-zero, but here k is this extra parameter in the exponent. Now, we have not discussed how I take something from y equals a times b to the x and write it as y equals a times e to the kx. We'll do that later. But for right now, you just have to take my word for it that we can do that. And it's worth our while to do that because it allows comparison between two exponentials much easier than otherwise. Okay. When I talk about these exponential functions, there's really two types. There's growth, and then there's decay. For exponential functions of the form y equals a times b to the x, we know it's growth if a is positive and b is greater than 1. And then it's decay if the a is positive and the b is between 0 and 1. Similarly, if it's in the form with e, again, if the a is positive, then the k has to be positive to be growth. And if the a is positive and the k is negative, it's going to be decay. Now, notice all of these rules I've given you are for positive a. What happens if a is negative? Well, just the criteria for the b switches. And the criteria for the k switches. Everybody okay with that? So it's basically all I need to do is look at the equation. I can tell immediately just by looking at the values for a and b or a and k respectively whether this is growth or decay. Let's look at a couple of applications and then we'll move on to talk about logistics. So here's a very common exponential problem type. It says, given that the population of a certain city in 1990 is 782,248 people, and the population of the same city in the year 2000 is 895,193 people, and assuming the population growth is exponential, in what year will the population reach 1 million people? So this is kind of a two-step problem. For step one, we want to be able to write our y equals a times bx equation because I know it's exponential, so I know that it's going to look like that. I'm going to actually change that to f of x. And in step two, we want to solve f of x equals 1 million. So if I start with step one, first thing I want to decide, I have two quantities in this problem. I have a date, like a year, and then a population. Which one of those should be x and which one of those should be y? i.e., which one depends on the other? I have a population and a date. Which one depends on the other? population depends on the date, right? I agree. So that tells me that if I look at this first piece of information, what I see is the point 1990, comma, 782,248. And my second point then is 2,000, comma, 895, 193. Everybody's good? Now, what's the problem with, what's unfortunate about these 2 points? Neither the exponent, or neither the x coordinates is 0. So I don't love that. So what I'm going to do, instead of thinking x as years, or the date, I'm going to define x as the years after 1990. So if I do that, 1990 turns into 0, and I'm super excited about that, because that makes my life way easier. And then 2000 turns into 10. This is a super common trick. It just makes your life a lot easier because you don't have to solve a system anymore. It just becomes, whoop, there's my A. And then to solve for B, I just have to do in one equation, one variable, which is not that big of a deal. To solve this equation, what would I have to do first? Divide by the 782. And after I've done that, how do I get rid of the exponent of 10? The 10th root is correct. And notice that I'm not going to write the plus or minus because I know that b's are always positive. So I'm going to discard the plus or minus, even though that's an even root. And it technically gets 1. To get this into my calculator, what I'm going to do is I'm going to type the number 10. Then I'm going to press math. I'm going to use command 5. That allows me to kind of pick any root I'd like. And then I can just type in that fraction 985, 193 over 782, 248. So the B is about 101, right? Now, the hitch here is that these exponential equations are really sensitive to rounding. And ideally, I'd like to keep all of the decimals for this value B that I just had. The easiest way to do that in our calculator is I'm just going to save that number as a variable name. So the way to do that is we're going to use the STO button, which is right above the on button. So the ant says it's just whatever this last number was. And I'm going to store that into the letter B because that was the letter in my equation. Don't use X, whatever you do. Oops, I missed the equal sign. So there, that's me storing it as B. So now what I'm going to be solving is 782, 248 times 101 to the X equals 1 million. Now, who remembers from your Algebra 2 class what you need to do to get an x or a variable out of an exponent? Great. Let's pretend we haven't learned that yet. We'll cover that later this chapter. So if I don't know what to do algebraically, how am I going to solve this? I'm going to graph each side of the equation on my calculator and find the intersection. So into my calculator, I'm going to go to the y equals. Into y1, I'm going to type the left-hand side of my equation. Instead of using 101, though, I'm going to use b. That's why I saved that number, is so I could do something like this. All right, now I'm going to set my window. Remember, X is the years after 1990. What should be the minimum X that I should be concerned with? Remember, X is the years after 1990. What's the minimum X I should be concerned about? 0, right? That's the smallest X in my point. Now, my X max, I know has to be bigger than at least what number? I know after 10, we're still not to 1,000,000, right? So I know X has to be at least bigger than 10. I don't know, I'm just going to guess at 30. Sound okay to you guys? All right. The Y minimum, what's the smallest Y value that I know my model's going to ever take? $782,248, right? This population is growing over time. The initial population is going to be the smallest it ever gets. Now, I'm not going to type that in because that's an annoying number. I'm just going to type in like 700,000. Is everybody okay with that reasoning? My Y max, I know, needs to be bigger than at least what number? What are we solving for? It's got to be bigger than that then, right? Because I need to be able to see that 1,000,000 line. So I'm going to do like 1.25 million. And now I'll hit graph. So here's the population curve being drawn in. Here's the line for 1,000,000. And I'm looking for the intersection. So second trace, intersect command, enter, enter, enter. And I get about 18.2. What's the unit for X, though? What did I define X as? Years after 1990. So the question asks, in what year will the population reach 1,000,000 people? How would I answer that? Because it asks for a date, right? Yep. So we'd say maybe during the year 2008, right? Probably in the spring, right? It's inside of the first quarter. So during the spring sometime, or I guess winter ends in February. I guess it could be, or I mean in March even, right? Still the beginning of March is winter. It might be in winter still. I don't know. Anyways, the first quarter of the year 2008, but I'm just saying during 2008 is okay. Now, the way this question here is phrased at the end matters. What if it asked, in the beginning of what year will the population exceed 1,000,000? What would we answer to that? Yeah, the beginning of what, or what is the first year, or that the population exceeds 1,000,000? 2009, right? Even though you'd think 18.2, let's round that down. We got to go up because it's growing. If I go back to 2008, the beginning of the year, it's less than 1,000,000. The first year where we exceed 1,000,000 is 2009. So just be careful at the way the question is phrased will really dictate whether we round up or round down. Now, even if this was like 18.9, if we asked during what year does it exceed 1,000,000, it's still going to be 2008, right? If it's 18.00001 and we say what's the first year it exceeds 1,000,000, it's still 2019 or 2009, right? Everybody's okay with that? So just be careful with the wording of the questions and make sure we really kind of think about the way we want to answer that. Now, over the short term, exponential functions do a pretty decent job of modeling things like population growth. But over the longest of long terms, not so great. Because if you think about as a population grows, eventually it's going to reach the carrying capacity. You're going to run out of food or resources or space or habitat or whatever, and that's as much as you can get. Or if you're working out in the gym, you start off, you make lots of progress, and then it tails off and you stop making a lot of progress. You know, like as you get real good at something, it takes more and more and more effort to get a little bit better at it. So a better representation often for things like this is called a logistic model. So a logistic model is of the form f of x equals c over 1 plus a times b to the x, or c over 1 plus a e to the negative kx. The nice thing about these logistic models is that they have two horizontal asymptotes, one at y equals 0 and one at y equals c. So if I think about like the graph of one of these things, what it'll look like is that where we follow the asymptote, we grow exponentially at the start when the population is low, but then it starts tapering off as the population increases, right? And even better, one of these logistic models, say we get like a sudden migration and the population exceeds the carrying capacity, it's just going to naturally dip back down and you're going to have population die off till you return to that upper limit. All right. Let's do a couple of quickie examples here using one of these things. So let's say we have the following exponential function. We're just going to do part A. So the horizontal asymptotes. We know one is always y equals 0, always for all logistics. The other is y equals c. The c in this case is 10. Everybody okay there? The y-intercept, we know every y-intercept has the x-coordinate 0, and the y-coordinate would just be f of 0. So when I plug 0 in for x, 0.06 to the 0 is 1. 3 times 1 is 3. 1 plus 3 is 4. 10 divided by 4 is 5 over 2. And there's my y-intercept. Everybody's okay with that? Why is the y-intercept often of interest to us? If this is a model for population, year 0 would represent the initial population, right? So that's why we're talking about y-intercepts there. It's like, it's an easy thing to calculate. Why do I care? Or like, what's the point of doing that? And it's like, well, it's, you know, oftentimes an important, like, real world number. All right, one more logistic example, and then we're on to the next thing. So here we're told the population of a city can be modeled using the logistic growth equation at P of t equals yada, 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 where P is the population of city T years after 1950. At the beginning, notice there, the beginning of what year? Ooh, will the city have a population of 1 million people? So here the model is already constructed for us. So like the step 1 doesn't need to be completed. All I need to do is solve this for P of t equals 1 million. To do that, I'm not doing it algebraically because, woof, look at that thing trying to solve that algebraically. No, thank you. I'm just going to use my calculator. I'm going to do it the same way I did before. So in Y1, I'm going to type in that logistic model that is given to me. Okay. And now I'm going to go to my window and think about what I have here. So 1950 is like year 0. I guess I could calculate the initial value here for year 0, but I don't really know. I'm going to just guess it takes a long time for a city. I don't know. I'm just going to pick x equals 100. Just if I have to make it, or the x max to be 100, if I have to adjust it, I have to adjust it. I know that the horizontal asymptotes are 0, and then 1,425,000. I'm too lazy to type in all those numbers. I'm just going to do 1.5 million as the upper bound there rather than the asymptote, because like that's a kooky number. I like round stuff. And I'm just going to hit graph. So here's my logistic curve coming in. You can kind of see the two asymptotes clearly visible. There's the spot where we have 1 million. Second trace, intersect command, enter, enter, enter. And I get 79.002. So how would I answer my question? So I round this up to 80, right? And then 1950 plus 80 is 2030. Everybody's cool? Again, the calculator is going to do a lot of heavy lifting for us early on here. Let it, right? Let it. If you have a ACT or something in the near future, you're doing another ACT this summer, as you juniors might be doing, remember that if you don't know how to solve an equation, you can just type both sides into your calculator and look for intersections, right? On a multiple choice test, when nobody's looking at your work, use your calculator. It's a really effective solving tool. All right, so in 15.2, we're not going to really do any new content. We're just going to look at a couple of specific situations, talk about the equation, the formula for that situation, and do some examples. Everybody's cool? All right, let's rocky and rolly. So the first situation we're going to talk about is the exponential population model. So that's P of t equals P naught times 1 plus R over 100 all to the t. P naught is the initial population. R is the percent change. And t is just some unit of time. So if we think about this as an exponential, A is like the P naught. The 1 plus R over 100 is like our B. Everybody see that? Remember, the B is what the exponent is too. Let's grab a quickie example. So here it says, decide if these guys are growth or decays, and then find the constant rate. So find the value for R. So what I want to do here is I want to start by identifying the b. I know in the first one, since the b is greater than 1 and the a is positive, this is growth. And then the second one, because the b is between 0 and 1 and the a is positive, that's decay, right? And then to find r, since this is b and this is b, I can say that 1 plus r over 100 has to equal 1.08 or 384. To solve that equation for r, I just subtract 1 from both sides and then multiply both sides by 100. I get that. NBD, right? The trick is recognizing that, oh, I just set the b parts equal to each other, and then I can solve. I'm not going to do part B, but what do you notice is going to be a little bit different in part B? What kind of answer are you going to get? A negative. Very good. So anytime you have a decay, the R value needs to be negative, right? That's an important point to illustrate there. All right, let's look at some examples. Okay. Determine the population model with an initial value of 15 increasing at a rate or a constant rate of 6% every year. So again, it says it's population, so I'm going to use that population model. It says initial value of 15, so that's my P naught. It says we're increasing, so I know the R is positive. 6%, so that's my R. And then I should make a note of what unit T is in. If I write T as just T, the unit has to be, how often is that 6% growth happening? Years. So if T is 1, how many times should that 6%, if T is 1 year, how many times should that 6% have increased? 1 time, right? So 1-to-1 between the number of times we get that increase in the number of years. I noticed that 1 over 100 plus 1 just simplifies down to 1.06. Now, what if I wanted to make T as in months? How much of that 6% change happens in 1 month? 1/12 of it, right? So my exponent should be T over 12. If T is months, right? If T was in centuries, it would be 100T, because it should have hit that 6% growth 100 times for the 100 years that have gone in a century. So depending on the context of the problem, if it's asking for, like it goes on and asks for something and then the answer's in, how many months since blah, 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 I'd want to write the blue equation. If it asks for how many years since blah, 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 I want to use the red equation. Just kind of depends on what else is being asked. Almost knocked over my drink. All right. Now there's another situation where we have to be a little bit careful. Let's look at this example. It says determine the population model with initial value of 15 increasing at a constant rate of 6% every 6 months. Isn't this the exact same problem? Yeah, almost. So we know right away that this part is going to be the same. If I say T is in years, what should the exponent be? Not t over 6. Not 1 over 6. Not over 2. How many times are we going to hit that 6% growth in 1 year? Twice, right? Because it's happening every 6 months. So it should be 2t, right? Because you're getting it happening twice. Like in 1 year, it happens 2 times. Now, if we wrote it in months, how much of that how much of that 6% change is going to happen in 1 month? If you get 6% every 6 months, 1/6 of it, right? So it should be t over 6. Because after 6 months, you should get 1 full change, right? Does that, you kind of seeing how to do this? And again, depending on what they asked me to do after this would justify what I wanted to do. It would even be okay for me to have done this. You know, where t can just be 6-month increments. Now, if it asks how long, that's kind of a crummy choice to make, because now you have to say, okay, I got 14.8. Well, now I have to remember to multiply that by 6 to turn it into months. But if they ask how many years, you know, like it's a conversion hassle. Typically, I'd want to use one of those two. And the context of the problem, what they're asking for, would tell me which one of those two is probably the better one to choose. Although all of them will work. It's just how much mucking around with units at the end do you want to have to do? You know what I mean? So that's, again, totally up to you. All right, another example. Says, suppose that a colony of 120 bacteria is put into a petri dish and the culture doubles every 3 hours. Predict how long it would take for there to be 400,000 bacteria. I read this and I see this as a 2-step problem. Step 1, we need to write our population function. And then step 2, we need to solve that for t when p of t is equal to 400,000. So let's start with the writing piece. What is the initial amount? How many bacteria do we start with? 120. What is the R? What is the constant rate of change as a percentage? Does it give us a number in here? Yeah, so it doubles. So I know that R is greater than 0, but what percentage does double mean? Not 200%. Not 50%. Let's think about it this way. So if I have 1 unit and I turn it into 2 units, how many units did I gain? 1 unit. What percent of the original did I add? 100. So what is double? 100%. Okay? Okay? And then what unit should I have t in? What do you guys think? I would do in hours. How much of that doubling happens in 1 hour? Takes 3 hours to double. How much doubling gets done in 1 hour? 1/3 of it. So I'm going to do this as t over 3. Everybody's good? Okay. So now I'm just going to plug this. Oh, FYI, what is 1 plus 100 over 100? 2, right? There's the double. When we see double, right? All right. Let's set this up then. 120 times 2 to the x over 3, absolutely. And then this should be 400,000. Window. I don't know. I'm going to go 0 to 100 again. I guess that seems feasible, 100. You know, I could try to count this out and see how many doublings it takes. But, like, I'm just not interested. The 100 is probably enough. The minimum, we're starting at 120 and then going to 400,000. I'm just going to do 0 to 500,000 or something. That seems, oops. I screwed that all up. That one was supposed to be the 500,000. Okay. And that ought to do. Whoa! Those bacteria are getting busy. There's my intersection. Second trace, intersect command, enter, enter, enter. About 35.1 hours. And this is nice because my unit was in hours, so I know it's just like straight hours. There's no conversion to do at the end. If I'd used just T, I would have had to multiply my answer by 3 because I would have had that many 3-hour segments. So times 3 would get me back to hours, right? Which would have been fine, but you have to notice that that's what you're doing, right? It is okay to do it that way, but you have to be careful. You have to remember that you know, that that's your plan. Very easy to forget. I like to reset it so that whatever my answer is just my answer, and I just have to write it down and I'm done. I don't have to do an extra unit conversion at the end, although it's okay to do that. The next situation we're going to look at is radioactive half-life. So those of you that have had a chemistry or maybe even an earth science class have probably talked about radioactive decay. Certain elements emit radiation. In doing so, they're losing mass. That mass is lost in the form of radiation. Typically, you measure how radioactive something is by the amount of time it takes for it to emit half of its mass as radiation. That number is called a half-life. The important thing for us is that R, whenever we see half-life, is negative 50%. It's negative because it's a decay we're losing, and 50% for half. Everybody's okay with that? Okay. But otherwise, it's like the same setup as our population formula. It's just that like the R is kind of fixed. All right. Suppose that the half-life of a certain radioactive substance is 35 days and that you have 10 grams of the substance initially. That's our P naught. Find the time that it would take only 1 gram remaining. So again, step 1, write my equation. And step 2, solve that equation equal to 1, right? So P of T, the initial amount is 10. R is negative 50. And then what should the T be? We're having every 35 days. I would say I'd want to represent T in days. So the exponent should be T over 35, right? Because it takes 35 days for 1/2 to happen. So 35 in for T is over 35 is 1. We do 1 multiplied by 1/2. That's what we want. Okay, so that'll work. Into my calculator this goes. So I have 10 times, and then 1 plus negative 50 over 100 is just 0.5. And then I have x over 35. And then this just needs to be 1. So if I think about this, 35 days is going to knock me down to 5 grams. Another 70 days will knock me down to 2.5. 105 days will knock me down to 1.25. And somewhere in the next 35 days, will knock me down under 1. So I would say like 0 to 150, because I know it's going to be at least 100 days to knock it down there. The Y minimum is 0. You can't ever get less than 0 grams of something. The Y max should be 10, though. That's how much I started with. So that'll do. The decay ones are usually easier because you know the start and the end. The end will always be 0. The start will always be the beginning. That's often easier to pick your Ys. Second trace, intersect command, enter, enter, enter. And I get 116.3. And I'm done. Okay. I think I have one more example. Yes. Okay, good. So you might be given you might have to use a logistic population model. You'll never have to create your own. I'll always give you the logistic model, and then you just have to use it to do stuff. So here it says you started a bunny petting zoo. Oh, that's cute. You determine that the population of bunnies on your farm can be modeled by the equation B of t equals yada, 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 where t is measured in years. How many bunnies do we have initially? What time is initially? 0. So I'm just going to do B of 0. So that gives me 800 over 1 plus 99 e to the 0. E to the 0 is 1. 1 times 99 is 99. 1 plus 99 is 100. 800 over 100 is 8. So we start off with 8 cute little bunnies. What is the maximum sustainable population for your bunnies? Well, that's the horizontal asymptote at y equals c. Well, the c is just 800. So 800 bunnies is the maximum that my farm is going to be able to support. C says, how long will it take for you to have 500 bunnies? Well, there I just want to solve B of t equals 500. To do that, well, I'm going to just use my calculator, man. I'm going to do the same graph and intersect thing that I've been doing the whole day. Okay. So 800 over 1 plus 99 times e to the negative 0.5x, and then 500. So I'll set my window. I have no idea how long this is going to take. I'll probably go down and do should be way less than 100, right? I don't know, maybe 20. And then the minimum, well, that's the y's are easy because it's just the asymptotes, 1 and 800. Let's hit graph and see what we got here. So here's my population of bunnies, my logistic curve. Nice S shaped there. There's my intersection. Ooh, that happened fast. Those bunnies are getting busy. 10.2 years. Yikes. So it took 10.2 years to go from 8 bunnies to 500 bunnies. They're not messing around there. You get it, bunnies. All right. Locked in. All right. So at this point, you guys should be able to do up through 36, unless you're a senior, in which you're responsible for none of that. You just work on your study guides. We'll do one more set of lessons for you seniors that you'll be responsible for on Tuesday. Whatever we get through there will be the last of the stuff you're responsible for on your exam. Juniors, we should expect to see a homework quiz next week. I suppose seniors, if you want to take it as an opportunity to improve your grade, you're welcome to do so. Sure.
Good afternoon. Let us pause where we are and quiet ourselves for prayer.
Why not?
In the name of the Father, the Son, and the Holy
I'd rather grade one more homework quiz and no
How have
exam.
I shown love to others today? Dear Father, you call us to love our neighbors as we love ourselves, and to treat others as we would like to be treated. Fill our hearts with your goodness so our actions become second nature and bring us closer to you. We ask this through Jesus, who is love for all. Amen. In the name of the Father, and the Son, and the Holy Spirit. Amen.